Hey guys, so we're going to continue now with the second part of membrane transport, and the idea here, we already said how we were going to divide the different types of movement across the cell membrane. Okay, so continuing forward, we have that simple diffusion is just the movement of a substance through the cell membrane from more to less without spending energy. And in this case, the main difference is because the substance tends to be very small and hydrophobic, they tend to pass through the cell membrane without any transporter. So they have an unassisted membrane transport. And that means they will move from more to less. Usually, we see this in small gases, small molecules like oxygen, carbon dioxide, as they pass through the alveoli in the capillaries and the tissues. And we can see some of these movements also with very small substances going through the kidney tubules. Again, I'm moving from more to less, and they can pass through the cell membrane without the need of any help. And what things makes diffusion go faster? These are the fixed law of diffusion. So the greater the concentration gradient, the more easily things may pass through the cell membrane. The more hydrophobic, the more permeable it is to the membrane, the more easily it will pass through the membrane. The greater the surface area, we are able to pass more through diffusion. The smaller the molecular weight of the substance, the easier it will pass through the cell membrane. And the smaller the distance, the easier we will have diffusion. Okay? There's a specific type of movement similar to diffusion, which is called osmosis, which is the net movement of water through its own concentration gradient. Here we can see from side 1 to side 2, we have two solutions. Side 1 is pure water, so no solute and a lot of solvent or water, and side 2 has less water and more solute. And because the membrane is impermeable to the solute is not able to pass, it's not able to diffuse the cell membrane, but water can. So water will move from an area of higher concentration or higher hydrostatic pressure to an area of lower hydrostatic pressure or lower water concentration. So in this case, water will move from side 1 into side 2, and this will permit the equilibration of the solute or the solution, So this is osmosis. And when we look at osmosis in the point of view of the cell, because the cell has a solution, a cytoplasm that has a specific concentration, if the solution where I put the cell in has the same concentration as the cell, let's say we have an isotonic solution, then there shouldn't be any net movement of water because we have the same amount of water outside and inside the cell. Usually the cell lives in a solution that's 300 milliosmoles. So we put a cell in a solution that's 300 milliosmoles. There's no net movement of water. But what happens when I put a cell that has lived in a 300 milliosmole solution, the concentration, and I put in a solution that has less solute, let's say 200 milliosmoles. So that means in this situation, the solution that has less solute will be more dilute, or another way is hypotonic. So water moves over there's more outside the cell into the cell, and that means that cells tend to swell. Well, what happens if I put a cell in a solution that's more than 300 milliosmoles, let's say 400 or 500? That means that this solution is more concentrated in the cell, so it's hypertonic, and that will mean that in this situation there's more water in the cell than out of the cell, so water will move through the cell membrane out into the cell, and so the cell will shrink. So cells in hypertonic solutions shrink. Again, cells in isotonic solutions stay the same volume. Cells in a more dilute situation, a hypertonic solution, swell, and cells in a hypertonic solution, more concentrated solutions, tend to shrink or crenate. Okay, so that's the main thing that we need to go over in that situation. Now, whenever I want to rehydrate a patient, if I give a patient a solution through an IV solution, that solution has to have the same concentration as my plasma for me to avoid either swelling or shrinking the cell. But if I'm giving a solution orally through the mouth, I usually give a solution that is going to have water, but also has some things like salt, sodium, chloride, potassium, glucose, etc. So that's a rehydration solution. And this is due because in the small intestine I have a type of channel, which is the SGLT1 channel, that permits me to reabsorb the solute, and who follows the solute by osmosis? Water. So I can rehydrate much better the patient by consuming solutions that have some solute instead of just consuming a solution that only has water. Okay? These parts is you can skip. The idea is that cells are able to compensate or to maintain homeostasis if we change them into different tonicities or concentrations. But that's basically it. And although we're not going to do any calculations, just be aware for us to calculate plasma osmolarity, we tend to calculate 2 times the plasma sodium, and that should be it. Maybe also, just to be very specific, we can also add glucose divided by 18 plus urea divided by 2.8, but you don't have to calculate that for your exam. Okay? Like we said beforehand, the total body weight, more or less 50 to 60% of that total body weight is water. Of that total water, of that percentage, of that 60%, 40% is going to be found inside the cell, and the other 20% will be found outside the cell. So here we're saying that 42 liters are found of total body weight. In this case, this is 100%. We say that 2/3 of it is found out in the cell, and the other third of it is going to be found outside the cell. Of that volume of fluid that's in the extracellular fluid, we know that part of it, 3/4 of it, will be found in the interstitium, the liquid bathing the cells, and 1/4 of it will be found inside the blood vessels or in plasma. Okay? So that's basically it. Although you don't need to know the specific number or calculations or values, just remember that the extracellular fluid we tend to have more sodium, more calcium, more chloride, and more bicarbonate, and inside the cell we tend to have more potassium than outside the cell. The concentration in both places, extracellular fluid and intracellular fluid, should be the same, 290 milliosmoles per kilogram of water. So we talked about simple diffusion and a subtype, which is osmosis. Then we're going to continue another type of passive transport, which is assisted membrane transport, which can be facilitated diffusion or carrier-mediated transport. Either way, the idea here is that we're moving things from an area of higher to lower concentration, but in this situation, we are doing it through a channel, through a doorway. As you can see here, it can be an ion channel, it can be a transport carrier, but the idea is something, because the molecule they're moving from higher to lower concentration is so large or too hydrosoluble, they need a carrier or a transporter to take them into or out of the cell. Okay? So facilitated diffusion, I move the substance from higher to lower concentration. I'm not spending energy in the form of ATP, but I do need to require a carrier molecule. Now, when I'm moving something from where there's less to where there's more, that means I'm moving against the concentration gradient. The other types, simple diffusion, osmosis, facilitated diffusion, is with the concentration gradient. In this type of transport, active transport, I'm moving against the concentration gradient. I need a protein carrier. I need to take things from less to more. This is active transport, and then I need to spend energy. If the energy I spend is directly on that specific channel, that's called primary active transport. Now, if I'm moving something from less to more, and I'm using the energy that has been spent by the primary active transport to move something from less to more, that's called secondary active transport. I here have an example of the main primary active transport that I want to talk about, which is the sodium potassium ATPase pump. So the sodium potassium ATPase pump takes sodium from where there's less inside the cell to where there's more outside the cell, and I take 3 sodium outside the cell, and I will move 2 potassium into the cell, again from less to more, from less outside the cell, more into the cell, and I will spend 1 molecule of ATP to do this. So it's a primary active transport. Secondary active transport will move things from less to more, but they will be dependent on the sodium potassium ATPase pump. So in the case of secondary active transport, I'm moving something from less to more, but I'm taking the things, let's say for example, taking sodium into the cell, and that substance from less to more into the cell. That's called co-transport because they're both going into the cell. While in counter-transport, I'm moving sodium into the cell, but I'm moving the substance from less to more out of the cell. So this is going to be counter-transport because I'm moving it from less to more, but in different directions. So again, in active transport, we have primary active transport, I spend energy directly. In secondary active transport, I take this from less to more, but by using the energy that has been spent by the sodium potassium ATPase pump. Finally, we have membrane transport, where we use the whole membrane to move something along into or out of the cell. So in this situation, vesicular transport, the material is moved into or out of the cell, but it's wrapped around the membrane. It's also a type of active transport, even though we're not going to calculate it as active transport. We have two types of vesicular transport. If I take something from out of the cell into the cell, that's called endo. The endo means inside. Cytosis. Cytosis, the membrane. I'm using the membrane to take things into the cell. Examples of this could be pinocytosis, while I take small molecules or substances or liquids into the cell, or phagocytosis, where a cell is going to engulf a bacteria or a very large molecule into the cell. And exocytosis, exo means outside, cytosis, the cell membrane, means I'm taking large substances out of the cell. So here we're going to see an example, give me a second, of endocytosis. So endocytosis, as we can see in this one, let me give you a second. And this one, and this one is endocytosis. In this case, it's phagocytosis because I'm taking a large molecule into the cell. In the second one, I'm just taking through pinocytosis or fluid-phase endocytosis, a small molecule or molecules into the cell. And in 3, I'm also taking something into the cell but needs to bind to a receptor. But either way, all these 3 are going to be endocytosis. While number 4, exocytosis, I'm taking something from inside the cell out of the cell. Okay? And a couple of other things. Just remember that the movement of water could be through the cell, but also could be by using channels called aquaporins. Aquaporins is a way we can move water into the cell through transcellular pathways. Remember, transcellular is going through the cell. It's going from one area to the other area, while paracellular is moving between cells. What's happening here? Okay. So this is just a couple of other things to remember. We have simple diffusion, which is not shown in this image. In A, facilitated diffusion, I'm taking from more to less using a carrier without spending energy. B is an example of primary active transport. I'm taking calcium from where there's less to there was more, spending 1 molecule of ATP. That's primary active transport. In secondary active transport, I'm taking sodium into the cell and calcium from less to more out of the cell. And this is thanks to the sodium-potassium ATPase pump. It's a counter transporter because one is going out, the other one is going in. In this other example here, I'm taking, in this case, chloride into the cell from less to more, and I'm using sodium to go into it. So in this case, again, it's depending on the sodium-potassium ATPase pump, and it's called co-transport because I'm going in the same direction. And lastly, be aware that we can see a difference with simple diffusion and facilitated diffusion. If this graph is measuring concentration, this concentration is 0, this is more concentration, this transport rate 0, this is more transport rate or faster transport rate. When we have simple diffusion, what we can see is, I don't know why it's doing this like this. We can see in simple diffusion, as I'm increasing concentration, I'm increasing the transport rate. That makes sense because in simple diffusion, I'm going through the cell membrane without the need or help of any type of channel. So as long as I'm increasing concentration, I'm going to be able to transport more into the cell or out of the cell, depending on the process. While in facilitated diffusion or carrier-mediated transport, when I have a channel or a carrier that's moving it, the idea is that because I have a certain amount of doorways that I have here, channels, there will be a point where all those channels are saturated. So I will be able to increase the rate of velocity of transport until a point where all the channels are being used up. And when I have this, what I will see is that the transport rate is not just going to decrease, it's just that it cannot increase anymore. So that's called transport maximum, when we have reached the maximum velocity of transport. And why? Because all the channels are being used. So with this, guys, we're going to finish this part and we'll continue later on with week 3. Thank you.